Welcome back. Our next speaker is Abbeel from UC Berkeley, and we're looking forward to his talk on deep reinforcement learning.
Thank you. Good morning, everyone. So a lot of my work is in deep learning for robotics, and the kind of prompt for today was to make a talk about representations in deep reinforcement learning. So first time I'm giving this talk. Let's see how it goes. Let's start with some background. Reinforcement learning considers a setting where we have an agent, which is the thing we want to find a good program for. The agent gets to choose from a set of actions. After taking an action, the environment will change state, will emit a reward signal, and then the agent acts on the changed environment, and this cycle just repeats over and over and over. And so what makes this fundamentally different from something like supervised learning is that the supervision here is in terms of how much reward you accumulate over time, rather than supervision directly on which action you should be taking, in which case it would turn back into a pattern recognition problem. So what kind of problems can you model this way? Robotics, where a robot chooses an action, world changes, takes the next action, repeats. Dialogue, when you have extensive dialogue with people. Logistics, gameplay, and so forth. Anything where after you take an action, the world changes state, and you have to act in the changed environment that you caused yourself. Here are some recent success stories and some slightly older success stories. So top row, what do we see here? From Pieter Stone's lab at UT Austin, the Robocop IBOs that learned with reinforcement learning how to control themselves to run faster than the other IBOs that they play against. Andrew Ng's group at Stanford, helicopter control, Russ Tedrick's work at MIT, control for a biped walker, and Jan Peters in Germany on swinging a ball into a cup. These are hard control problems, and learning enabled to solve these problems, and otherwise maybe it would not have been possible. These use somewhat traditional representations where you do heavy feature engineering, you represent everything in the control policy or whatever else you're trying to represent, we'll get to that soon, with a set of features you design, and then only a few parameters you tune. Recently, there's been a lot of progress where the representations being used are much more open-ended. They're deep nets. They can represent pretty much any function. And that has allowed people to have success in learn to control an agent that plays Atari games, continuous control in simulation, continuous control in the real world, and also to play the classical game of Go. And so what we'll see today is we'll see some of the algorithms behind this and the representations that go with them. So it turns out in reinforcement learning, there's not just one algorithm, and we can't just say, oh, here's the algorithm, and now let's learn the representation for the thing that's sitting inside the algorithm. There's many, many approaches to solving the problem. Broadly speaking, there is policy optimization and dynamic programming. Policy optimization directly considers a control policy and tries to optimize it and gets the best performance on the task. Or tries to get the best performance on the task. Dynamic programming tries to decompose the problem over time into pieces and solve for a solution based on the temporal decomposition. Based on these different approaches, these different kind of fundamental approaches, there are different algorithms that emerge. The ones I'm going to look at today are policy gradients, actor-critic methods, and Q-learning. Actor-critic methods actually bring together both policy optimization and dynamic programming methods into one. And Q-learning is just dynamic programming. OK, so this is the talk outline. I'll cover the algorithms, then we'll look at the representations that are underneath these algorithms. We'll look at some representations used for exploration, and then we'll also look at somewhat different algorithms that have emerged that have different representations underneath that don't exactly maybe fit the classical paradigm. And then at the end, we'll also look at algorithms that are yet completely different, that in some sense we try to learn the algorithm completely rather than still designing the algorithm. And so that's a very different approach than the most successful ones so far. OK, so in policy optimization, we have this policy pi theta, which defines which action to take in a given state. It's parameterized by a vector theta. We want to find the best vector theta. So this could be a deep neural net with many free parameters. And the objective is to find the parameter vector that maximizes expected sum of rewards over time. Expected sum of rewards because often the environment is stochastic, and so you can't maximize deterministic rewards. You maximize what an expectation you're going to get. Often the policy itself is stochastic too. That can be a good thing. Even though very often you can show that the optimal policy would be deterministic, a stochastic policy can help you with smoothing out the optimization landscape. So you might start rather high entropy with your policy, and then over time, entropy will decrease, and that will help you find a better policy. OK, so one of the standard ways, maybe the most common way to compute a gradient for your policy is the likelihood ratio policy gradient method. And the beauty of this method is I actually don't need the dynamics model of the world, and that'll fall out in a little bit. So when we have a sequence of states S0, action U0, and so forth till last time capital H, we'll have rewards at each time step, and we'll summarize the whole thing with a trajectory variable tau, and we'll say, OK, we're trying to maximize utility as a function of our parameter vector theta that parameterizes the policy, which is expected reward associated with trajectories times, and this is then the probability of following that particular trajectory. So this is what we're trying to optimize for, and later we'll redecompose it into states and actions. OK, let's take a look at what we can do here. We're trying to optimize this objective. We want a gradient to know in which direction to step. So this would be the gradient that we're trying to compute. Next step, we're going to bring the gradient inside the summation. Then we play a little trick that we can play in hindsight that might be a little puzzling right now, but it'll help us. We multiply and divide by the same thing, probability of a trajectory, put that in front of the gradient. Now what we can do is we can bring this underneath the gradient, and what we have here is the grad of the log probability of the trajectory. And so this is the expression we're going to work with. Why do we put it into this format? There's several reasons. The reason that we can already see right now is that we have an expectation now. This is an expectation, so we could sample and compute an empirical average of this expression. We can sample according to the current policy, which will effectively take care of this expectation up front. And this, we then have to compute along the trajectories to get our empirical estimate of the gradient. So that gives us this equation over here. So this is the likelihood ratio policy gradient. But we're going to do a little more to bring the states and the actions back into this.
So, question. Can you say that in words? What is that trying to do?
OK. To say this in words, what is this expression doing here? The gradient is saying grad log probability of trajectory, tau I, times reward accumulated along trajectory tau I. And so what this is saying is that if the reward is very high, so hold on. If the first term says point in a direction that makes the trajectory you just experienced more likely. The second term says how good that was. And so it's saying I want to move in the direction that I just experienced, more likely along trajectory I just experienced, and how much more likely depends on how much reward was accumulated. So this is a little tricky. It's rather imperfect, because if your rewards are always positive, no matter what you do, then no matter what you experience, you want to increase probability. But for some not so good ones, you'll increase the probability less. Then for the better ones, we will increase the probability more. And so that'll average out to put more weight on the better ones and less weight on the not so good ones.
How do you ensure that it's probability? Do you project back onto the simplex, or?
How do we ensure what is a probability?
P is indeed a probability.
OK, so P here, we're not going to represent directly ourselves. P is, for now, just a mathematical entity. That is, if we have a policy, we can run rollouts from that policy, and that generates a distribution over possible trajectories, and that's our P tau theta.
I understand how you get P by rollouts, but how do you get the gradient?
We'll get to that on the next slide. That's a good question. Yeah. We can't compute this directly just yet.
I see.
What's beautiful about this, though, is that it doesn't matter whether R is continuous or discontinuous. You can have 0, 1 rewards, only a 1 when you reach a destination, 0 otherwise, and this still works. And by having stochastic policies, actually, the landscape can be smoothed out even in this kind of reward landscape. OK, so the intuition that we just talked about is that, let's say you had 3 rollouts, and one of them is quite good, one of them is medium, one of them is pretty bad. All of them will increase their probability with this update, or that's what each term is trying to do, but more so for the better one than the not so good one. If there are negative rewards, then you could also end up decreasing probability of certain paths. Okay, so it never, interesting observation here, it never tries to move paths. So a lot of gradient methods will say, if I had changed my actions, then what would my path have been? And I should take a step in some direction to change my path. It's not doing that here, it's just shifting probability mass from some paths that are not so good to paths that are better. Now let's decompose this so we can actually compute this gradient. So grad log probability of trajectory I under parameterization theta of the policy. This is the probability of the path. It's probability of next state given current state in action times probability of action given state, and then multiplied over all time steps. Bring in the log, decomposing this. We see that this term here does not have theta in it. It's just dynamics. There is no parameter vector theta from the policy that participates here, so it disappears. And we're just left with grad log probability of action given state summed over all time steps. And so we can see that we can actually compute this without access to a dynamics model. All we need to know is our current policy and what the probability was of action given state for actions we took in states that we experienced. And so this is the full equation. We have sum over all time steps, grad log probabilities of action given state. That's just a grad log p. Of course, they need to still multiply with reward that was experienced. So we have this expression, substitute in grad log probability action given state for each time step, for each rollout, times reward associated with that rollout. Now, this is still pretty naive. It's going to be very high variance. And the reason this is still naive is things like, for example, this is the reward of the entire trajectory, but an action you take right now can only influence future rewards. So there's really no reason that you should be multiplying in all reward experience along a trajectory. You can do it. On expectation, this is OK, but it's very high variance. So to reduce variance, you can actually just sum over future rewards after the current action to get a better expression. Then you can do something even better. The bad thing about this is still, in the simple case where all your rewards are positive, that you try to push up probabilities of everything that you experienced. But some things are worse, some things are better. So ideally, you would compare with some average. So a simple thing to do would be to say, I'm going to compute from time t onwards how much I get on average over all experience I've had from t to capital H. On average, how much did I get? And subtract that out from this sum of future rewards. And so now you're centering it around some average. And what will happen is the better than average trajectories will get their probability pushed up. The actions along those paths will get their probabilities pushed up. And the worse than average will get their probabilities pushed down. So that is the likelihood gradient estimate. OK. So what does that look like in an algorithm? We initialize our, these days typically some deep neural net that represents the policy with some vector theta 0 for all the weights. Then we collect data under that policy. Then we perform a policy gradient update using the gradient that we just saw how we get to this. It's increasing probabilities of actions given state proportional to how good those actions are relative to average. And we can repeat this. And actually, this will work. It might still not be super data efficient, but it is going to move in the right direction. If your batch size is large enough, it'll take steps in the right direction and keep improving. If your policy is sufficiently stochastic, you'll have some exploration incentives. You'll see things in the world, and you'll get signal to go where you're supposed to go.
Peter?
Yes?
Can you roll back and say,
Sure.
what does these shortcuts imply or simplifications imply on the original objective that you started with?
OK, so on this slide, the things that we introduced. So if we go from here to here, that is a variance reduction. What it means for the original objective, the way you can do a complicated derivation to get to this, or you can just redo the derivation I showed to you, where from the beginning you look at sums over rewards over all times, and you'll see that then only the future rewards will contribute, and it'll automatically end up with this. So that's the simplest way to get there. You just have to go through the exact same derivation, but from the beginning, put all the summations over time in there. The subtraction here, what this is doing, this is saying, for an expression of this type, grad log probability, action given state, times something, the expectation of what's sitting up front here, expectation of a grad log probability is multiplied with a constant is equal to 0. So you can, whatever you multiply in here, as long as it's constant, which means it doesn't depend on the trajectories that you just experience which is slightly violated here, but in practice people will often do it this way. But there's a slight violation of that here. But if you make this not, if you use this equation, but if you make this a constant vector, then it's an expectation 0 change that reduces variance.
But you don't actually mean this is equal.
Yeah, so that's a good point. On expectation. So on expectation, these are all equal. Yes. This equal sign should be on expectation. All of these are equal. But if you do a sample-based estimate, they will actually differ. Thank you. Yeah. So then the question is, can we do better than this? The big place where we can do better is this subtraction here of just average of what we experienced. And so we can replace that with a value function. What is a value function? A value function is something that says for a given state, if I act according to my current policy, on average, how much am I going to get? And it can use a function to represent that rather than just recent rollouts. And so it can generalize from the past data rather than just using the current rollouts to get an average. So we're going to introduce this vpi, plug it in over here to get better efficiency. What are these values? How can we estimate them? So this is called the Bellman equation. What is this saying? It's saying that the value under a policy pi of being in a state S, which is the expected sum of future rewards, is equal to an expectation where you sum over actions and probability of that action in that state, sum over next states you might experience, probability of landing in that next state, times reward you experience on the first transition that happens, plus some discount factor times the value at the state that you end up in. So it's just a dynamic programming equation saying current value is equal to immediate reward plus value after that. For high dimensional spaces, let's start with low dimensional space where you can just enumerate states. Then you can just cycle through this equation over all states many, many times, and it'll converge. You'll have a table that'll have the values of your policy pi for each state. If you have a higher dimensional space, you can't cycle over all states. And so what you would do is something like fitted value iteration, where you initialize, let's say, a neural net with some initial parameter vector phi 0. You collect data from your current policy, and then you run this fitting procedure. What is this doing? It's saying, sample-based, I experienced a sample SU S prime R. On that sample, I had a reward, a future state S prime. My past estimate of the value function says what the value is at that future state, and my new estimate, v phi of s, is supposed to match up with that. So the new estimate is supposed to be as good as the estimate that does one step of look ahead, and that's the procedure you go through to find the better phi. And then there is some regularization. You don't want to jump around too much, so you want your next phi to be close to your previous phi I. And so if you iterate this over time, under some reasonable assumptions, you will find a pretty good value function, v pi. There can be issues if your representation is not rich enough, that you just can't represent the values, and you'll have a lot of issues. If you have a rich representation, this in practice will work quite well. So that gives us then the Actor-Critic algorithm, which combines policy gradients and value function estimation. What does it do? We initialize a policy architecture, some neural net, let's say, a value function architecture. We collect data according to the current policy. We update the value function estimate with the equation I just showed, and we can update the policy with the policy gradient that we saw on previous slides. And note, to avoid the tricky issue with depending on the current data, when you put something in here that you subtract, it's explicitly here subtracting based on only the past data. It's only using v phi I, not v phi I plus 1. In practice, still, people will often use v phi I plus 1 because it's more data and it's not that bad to be a little biased. But to be technically on expectation right, you need to just use phi I here, not phi I plus 1. Okay. And then you can actually generalize this even more. If you look at the equation up front here, the sum over future rewards, that's still just the sample estimates of future rewards. You can imagine that you replace that with current reward plus value at the next state, and that would be a lower variance estimate of what you want. Or maybe current reward plus next reward plus value at the next state, and taking an exponentially weighted average of all those different estimators is what the generalized advantage estimation procedure does. So using that idea, you can get actually pretty low variance estimates here of this gradient and get quite good performance on some challenging tasks. And I'll show that to you in a little bit. Any questions here? Because this wraps up the policy gradient and Actor-Critic.
Yeah, so apologies for the layman question, but after each iteration of updates, do you get more data?
Correct, yes. So there's a cycle that's happening here. Collect data, fit, and you repeat this till you get some kind of notion of convergence. I will say there's not very strong guarantees here per se, but that's the procedure that people will use.
Question.
Yes?
So it's 5 the parameters that you use to parameterize the
Correct. Phi parameterizes the value function, and theta parameterizes the policy. The policy maps from current observation to distribution over actions. The value function maps from current observation or current state to value of that state. Yes?
It seems that the value function also depends on the policy, right?
Yes. So what you're fitting here is the value of the policy pi that you're currently using. And so this is a moving target. So you would collect data under your current policy, fit the value function. Your policy would get updated. And even if you collected infinite amount of data here, and you perfectly fit your value function based on that, it's still get very, very close. You'll still change the policy here, and you'll have to redo things. In practice, people don't get a whole lot of data here, just a moderate amount, update the value function estimate. The policy changed a little bit. That's also because the policy only changed a little bit. The values only change a little bit also, because we're assuming stochastic policies. So small perturbations will mean small changes on expected value. And so that's why we also stay close to what we had before.
I guess I was asking whether the value factor in the parameterization is should depend on the policy in what way? Like, if you parameterize the value function, how does it depend on the policy?
So you could, in principle, do something where the value function takes in the whole policy and says, I'm going to learn to estimate value based on current state and policy being used. I think it would be very interesting to try. I don't think anybody has tried it. It's a little tricky to take in a huge neural net and parse it and output something, but maybe there's maybe a lower dimensional representation. Maybe you can project the policy onto some lower dimensional embedding where most parameter vectors end up, and then take that in as an extra input and learn values more quickly as your policy changes. It would be very interesting to try. Yes?
So the data collection is using the current policy. So how
Correct.
do you deal with the explore-exploit trade-off here?
So the way it deals with that, there are different things you can do. So the simplest thing is that the way you parameterize your policy, and this is very often used, is that you have an entropy scheme over time as your iterations progress. And so you force your policy to have a certain entropy level. And at the beginning, the entropy will be quite high, and the randomness in the actions gives you exploration. It's not very good exploration. It's extremely slow, especially in high-dimensional spaces, but it is often done that way. Better things that we'll really briefly look at is inserting exploration bonuses. And I'll get to that in a couple of slides. Yes?
Related to that, so since it's, the log probability is just a scoring function, right?
Correct.
Why not contrast two different trajectories, for instance? And say, okay, here are two trajectories. One gave me a higher reward, or similar to, the similar ideas that often, work in supervised learning. When you look at pairs, triplets.
So let's see. I haven't thought about that before. Not sure if I can get a good answer on the spot. But I think it is worth thinking about if directly contrasting trajectories could do better. There is a notion of directly contrasting trajectories happening because of the subtraction here of the value function, but it's somewhat indirect through looking at the value function rather than looking at two specific trajectories and comparing them. The original estimator even more directly looks at the trajectories because it uses average future rewards from a current time step. So I think these things are getting at that, but not in the exact way that you're proposing. And there might be something that can be done that's not being done yet by more directly zoning in on pairwise comparisons. I'm not sure. Other questions? Yes?
You said that in practice people use a moderate amount of data for each iteration. So one extreme, of course, is to just use like one tuple.
Mm-hmm.
Some of the earlier actor-critic methods were coming from the stochastic approximation. So what are the decisions that in practice?
So you do have to make a decision here how much data you collect. It's not clear yet how much data you really need to collect. It's easier to get things to work if you collect more data because the whole approach is more stable and it's easier to debug it. It might be that the optimal thing to do is not to do that, but because you might be more data efficient by always updating after every experience. It's just that in practice, a lot of the work has been towards stabilizing these algorithms and making it easier to get results out rather than being maximally data efficient. I think there is a lot of room there for improving that, but that's not been the things that have worked best so far. Yes?
So on a similar note, like, I mean, is it useful to say, like, to batch your collection where you like fix S and like a whole bunch of data on S to various S primes, or do you want to get the whole space?
So actually, that's a good question. So the trust region policy optimization paper, which we wrote 2 years ago, actually the initial premise that we wanted to investigate was exactly that. If you can reset into states that you experienced and re-roll out from there, does that give you a higher signal-to-noise ratio than if you just roll out from the beginning every time? Turns out that was not part of the paper ultimately, really, because we couldn't get that to work. I still think there could be something there, but maybe it needs more careful decisions on which states to re-roll out from. We were just randomly re-rolling out from states that were experienced, but maybe if you have some kind of information theoretic consideration saying this state is particularly interesting, we should re-roll out from this state, I think that's actually something worth revisiting and seeing what happens. Absolutely. But the naive version didn't work. Yes?
Yeah, the question about the rate that the environment might adapt or change,
okay.
And in relationship both to the amount of data that you collect and also in relationship to how quickly learning converges to some sort of nice spot. Because it seems like if the environment itself is adapting very quickly, you may never catch up. Depending on say how fast learning is.
Yes. So the typical reinforcement learning setting, even though it's advertised as adaptive and so forth, it's true that it tends to be more tailored to environments that don't really change, don't change too quickly.
This may be particularly insidious in the case when the policy that you're using a deep model.
Or more has to be learned. Yes. So my hunch for that would be to go back to a suggestion over there and to somehow estimate something about the environment that you feed as extra input to your policy or to your value function, such that as the environment changes, it's actually part of the state that you have some estimate of what the environment is like right now that might allow you to adapt more quickly. I haven't seen anybody do that, but that would be my inclination if you wanted to still get it to work when intrinsically it would adapt too slowly if you didn't do anything extra beyond this. It seems worth trying. I mean, a special case of this is also situations where you have adversaries who might adapt to you. Once you do something, they figure out how to play against you. And so then, again, maybe you need to very quickly understand what their new strategy is and feed that as part of the input to your policy or your value function to understand the value and the right action in the current state.
That may be different. Like you could have an adversarial environment versus just an adapting environment. Because randomness is usually the way to beat adversarial environments, whereas not being random might be a way of rapidly adapting to changing non-adversarial environments.
Yeah, so I don't think anybody's really pushed the limits of let's put this RL agent in an environment, and there's a tuning factor of how fast this environment changes from one type of environment to another one, and see when, essentially look at the learning curves or performance curves, let's say area under the curve of each of the RL methods as a function of that tuning variable of how fast the environment changes on you, and see what leads to big decays in performance versus when can it still keep up, and whether some algorithms are maybe better at keeping up than other ones. I think it's completely future work at this point. But yeah, I would say it's very worthwhile. Other questions about this? Already got 4 future papers or theses here. It's going fast. There's another approach called Q-learning. In Q-learning, instead of representing the value of a state, you present the value of a state and action combination. So you're saying, what is the expected value if I'm in the current state S, were to take action U, and from then onwards, for Q star, act optimally. Of course, we don't know what it means to act optimally, but we're going to try to represent the Q value for current state and action, assuming after that current action we act optimally. The current action does not need to be optimal. It could be, it could not be, but the assumption is then onwards optimal. You can again decompose this with dynamic programming. You can say the Q value for SU is sum over future states probability of landing in that future state times reward you get for the first transition there, plus then whatever the optimal thing is in that next state S prime. Okay, so once we have this, if you have a small state space, we can again just loop over all states and actions and do updates and find the optimal Q values. This is you can use this as an iteration where you use the right-hand side to update the left-hand side, and this will converge for finite state and actions. But in practice, we have very large state spaces, large action spaces, so we need to represent this with a function approximator, and so it would look something like this, a lot like the fitted V iteration. You initialize your Q value function, you collect data, and then you update your parameter vector phi that parameterizes your Q function by solving this optimization problem here, which is looking at all experiences you had and see on each experience how well is this equation satisfied with a squared penalty on dissatisfaction of the equation. And so this side of the equation uses the Q function we have computed so far, and then this side uses the Q function we're trying to learn right now as an improved version, an improved Q function compared to what we had before. And then this is just ensuring that we don't move too quickly in the space of Q functions. So that would be fitted Q iteration and things like DQN, which was the big results by DeepMind on Atari, essentially run this with some special schemes on deciding what to include into the summation here. You don't look at all past experiences, but actually in QLang you can in principle look at all past experiences. So they resample from the past, use things here based on that resampling strategy, and they also then have a strategy on how often they want to update the parameter vector versus collecting data. There is an interleaving of this update and collecting data going on, and then only after a while is the update reincarnated here into the left-hand side of this equation. And that's what they did to stabilize this process. So questions about Q-learning? Yes?
Why is there no discount parameter on the Q?
Forgot to insert it. Yeah, sorry. Yeah, thanks. Should be a gamma right in front of the max here or after the max. It doesn't matter.
So, I have a question.
Yes?
Do you have a simple explanation for why Q-learning is unstable in general?
Why it's unstable in general? Well, if it's a tabular setting, it's stable. Why would it in general be unstable? There's a few things that can happen. So if you do this update in the full space, it's a contraction. It brings the Q values closer to the optimal Q values. But then when you do this calculation here, which is a 2-norm based projection onto the function space that you're able to represent, that is not directly compatible with this contraction that's happening over here. And it could actually expand what you have over there if you have a bad function space. But then if your function space is large enough, then actually that does not tend to be much of an issue. You don't expand again, and this might work. But of course, if it's very large, you might not generalize well. So you need a lot of data to make sure that this projection here is something that generalizes well rather than overfits to the few samples that you have. So that's one aspect, that this thing, in principle, can expand rather than contract. The reason that's not an issue with value fitting is because in value fitting, what's happening in here in the projection is just looking at V pi, and it's looking at a sample distribution from pi, and it turns out that if you do that, you still get something that's a non-expansion that's compatible with what's happening here. But here with the max in there and the 2-norm, it's not guaranteed to be compatible. Of course, if this does nothing, if it keeps things in place, which you would have almost true when you have a very large function approximator, then it's not going to expand much or maybe not at all. There's another reason that this thing can sometimes do poorly, which is if you look at what's happening here is you're taking the max, and let's say your Q function is a little off, and some values are a little higher than they should be. Well, whichever one happens by random noise to be higher is the one that's going to be picked. That one is going to be propagated, and then the one before is going to be higher than it's supposed to be. And so there's a little bit of a bias towards increasing things. And in fact, if you look even at the very successful Q-learning runs where if you actually look at the Q values, if you run something like this, the Q values are way too high. Like if you could do rollouts from your policy, see how much reward you get. You could look at the Q values that it came up with. Even though it describes a good policy, the estimates are much too high. And so there's something called double DQN where you keep around 2 Q functions. You compute the argmax from one. When you do this max here, you compute the argmax from one and then use it to get the max from the other one to not have that upward drift as much, and that helps quite a bit in avoiding that. In the tabular case, I think the only thing that keeps this from drifting up is that there's a discount factor in front of it, gamma, that trims it back down. There's another question over there.
Yeah, when you've got the collect data set in this case and also in the previous slide, is that from like one run of like making decisions? What happens if you get stuck in one place, or is there kind of like a...
So typically...
For example, if you have a goal state you get stuck in or something like that.
Peter, could you repeat the question, Sue?
Sure. Okay. So the question is this data from one run? And maybe if you have only one run, you might be stuck in a goal state, and there might not be much interesting happening in that run, and then you might overfit to that one run. That is a real issue. And so if you do this from one run, then your lambda will be very high, and it will regularize very heavily to stay close to where you were and not change your Q function a whole lot. If you have more data, then you'll allow yourself to move a little further. The trust region policy optimization that we looked at looks at this very explicitly in policy space. It looks at the policy you use is based on this Q function, or it could be based on the policy that you're training and the value function that you're training, and you can look at what the parameter update has as an effect on how your actions would change based on that update, and it keeps it small, so your action distribution on your past experiences that you just collected wouldn't change too much, and that's a way to contain that you overfit to the current experience and maybe go somewhere where you don't really have the data to support that you should be going there. I would say in general there's a lot of kind of just unknown about exactly how much data you should have here and do updates here, what's the right thing to do. What is true about Q-Lang, which maybe I should emphasize a little more, is that you can use off-policy data. The way this is structured, the way it works out is that you don't have to use just the data from your current Q function to update this, whereas in the Actor-Critic, you kind of have to do that for things to be proper. Here, you can use any past experience and replay it in this summation here in your loss function, reuse it. And so that way, Q-Lang can often be more data efficient because all the data you collected in the past can be reused now. And effectively, what you're seeing is you're learning about your dynamics model through these values and replaying that in here to learn more data efficiently than the Actor-Critic methods. Not necessarily computationally more efficiently. In fact, computationally often not, but data experience-wise, it would be. Yes?
So what's the state art for exploration in Q-learning, and how do you compare that to Actor-Critic?
Let me get to that in a couple slides.
Can I ask another question?
Sure.
You said the money equation is a contraction equation.
Mm-hmm.
The contraction factor must be the discounting factor.
Correct.
If the discounting factor is high, it means that if the reward comes very late or something like that. So in the end, is it better than doing the policy gradient on episodic data?
So if the reward comes very late, and so you need a high discount factor to even see it, the problem becomes a lot harder. The problem will be much harder to solve no matter what algorithm you're using. In terms of differences between the approaches, it is true that if you use kind of any of those approaches actually will have trouble. You'll probably need something else. If you have very delayed rewards, you need explicit exploration incentives that help you explore the space, or you need hierarchy in your architecture that says, I'm going to set some goals, and then another goal, and the combination of setting goals leads to something underneath, achieving a sequence of things that gets me somewhere. And then at the high level, the signal is not that delayed because they only need to set a sequence of 3 goals to get somewhere. But the low level still takes a long time, but can get rewarded by achieving the goals that were set intermediary. So that would be the kind of things that would be needed to get it right. It's fundamentally hard if the reward is far out if you just use something like this. OK, so we've seen the 3 main algorithms. We've taken a little longer than I estimated, but that's fine. We fully understand those 3 main algorithms now. What it will mean for the remainder of the talk, I'm going to give you the hints at what is going on there rather than ensuring we understand everything, because then we're only going to get halfway and not see the full picture. So DQN used a component, 3 conv layers followed by 2 fully connected layers to represent the Q function, was able to learn to play Atari games at human level, beyond human level, for about 2/3 of the game beyond the human level, 1/3 not human level. The horizontal axis is 100% means human level. So that was very impressive, very surprising result that this was possible. Then TRPO plus GAE is an actor-critic method. What it does, it uses essentially the same network, but instead of outputting Q values here, it'll output probability distribution over actions. So this is the policy, and you use same network again to also represent the value function. It'll just output one value rather than a set of values, and that's used to subtract out from the sum of rewards, as we saw in the policy gradient equations. Also works well. It's easier to stabilize this because you can put a trust region on the policy, but it takes a little more data. A3C, so this was done at Berkeley. A3C done at DeepMind essentially merges these two into each other. It says if you're going to represent a policy and a value function, they need to reason about the same world. They need to reason about the same images. So just squish this in there and have one big representation. And then there will be an extra output here that's the value. And so they can share things that they learn, and that way learn more quickly. The dueling network architecture makes it even more explicit. This is a Q-learning approach where the Q function, this would be the standard DQN Q function. Instead of representing the Q function this way, what's tricky about this is that if you think about what is in that Q function, you're trying to differentiate between different actions. Which action is better than which other action in the current state? But the value of a state, the Q value of a state, is dominated by the state itself, not by the specific actions. And so what's happening is that you want to understand the differences between actions, but really the signal is dominated by the overall value of the state. Makes it a hard learning problem. In the dueling network architecture, they explicitly separate this out. They have, after the conv layers, fully connected onto value explicitly here. And then here, the advantage function, which is the difference between Q and V. It's the difference between the Q value of a state action pair and the average value in that state. And that's being learned over here. And then combined, you get the Q function again. This allows to more directly zone in on the values separately from the differences between actions, and allows to learn more quickly than the original architecture. In fact, a lot of the best results current best results in terms of data efficiency and so forth are dueling architecture with this trick of double Q learning to stabilize that. You take an argmax and then a max from another network.
Question, what's the dueling here?
The dueling, what they refer to is that there is a V network and an advantage network, and they both contribute to the Q function at the end here, and they're essentially dueling for the attention of the Q function because they share everything here, and so they need to somehow share what's happening here, and they'll both contribute gradients that go back in here, and so who gets more from what's there, that's what they're dueling about.
There are normal rules of backprop.
Normal rules of backprop, yes.
No adversarial nothing.
There's no actual adversarial aspects, though in principle, you could carefully think about whether you might want to rescale these gradients coming from this one versus this one. And some recent work that we haven't published yet actually analyzes that certain rescalings here are actually the right thing to do, and other rescalings are not the right thing to do to make things work in a more stable way. So you can also use this for continuous control, for example, controlling a humanoid or a spider robot. This is just in state space, so it's a lower dimensional network. 3 hidden layers, 100 units, 50 units, 25 units. Input is state, output is torques at each of the motors. And so if you use TRPO plus generalized advantage estimation, which is an actor-critic method, you can get learning like this, where, of course, initially it doesn't do very well because it doesn't know what to do. Has a randomly initialized neural net, about 100,000 parameters. But then over time, as it updates its policy, and when I had an I index in the past slides, that's the iteration index here. We have now theta I equals 640, phi I equals 640. It actually has learned to stably make progress. And the reward here is as simple as the further north, which is this way, the better, and the less impact with the ground, the better. And you can then deploy this on a different robot, let's say a spider robot, run the exact same code, and it'll just learn to control the spider. Of course, initially it doesn't know what to do, but over time it figures it out. And I think some of the things people alluded to, imagine the robot were to change over time, then if you had knowledge about what parameters in the robot are changing, maybe lengths of links, maybe some friction parameters and so forth, then you could potentially feed those in together with the state and learn a policy that will generalize across those. If you don't have knowledge of that, then you could do something like running a recurrent neural net that effectively does system identification on the fly and feeds those in. Here, the reward function is how close the head is to standing head height. So this is kind of half as good as it's going to get. And this is all with random exploration. There's nothing here except for randomness that happens to get it a little better than before, and over time it gets a better policy. Now these rewards are pretty well shaped. It's not reward of 1 for standing head height, reward of 0 anywhere else. It's a reward based on distance to standing head height, reward based on how far you go that way. So you get signal from the beginning. If you randomly move around, you get to see something about what's good, what's bad. We also looked at this for robotics. Can we solve robotic manipulation problems this way? The first thinking would probably be probably not, because the amount of data required for everything I showed to you so far is completely impractical. But we played some tricks to get this to work. Part of it is the architecture, so let me emphasize that part here. What's happening is there's about 92,000 parameters. The first layers are conv layers, so that's kind of the typical thing. You kind of just process RGB values with a mask and feed that through. But then there's a bottleneck layer here. You can think of it as an attention layer. It looks at all the conv filter responses at conv3. There's 32 filters. And for each individual filter, it checks where it is most active and extracts the coordinates of that. So essentially extracting 32 pairs of coordinates in the image and passing that on to the motor control. So that's an information bottleneck that we know a priori that to do control, probably you need coordinates of things in the image. And we explicitly put that in here. And that helps a lot in terms of quickly learning this whole thing end to end. So with this system, we're able, and we play one more trick, which is we learn actually 2 things in parallel. We learn one controller that has access to state, and another controller that only has access to the images. The one that has access to state can learn more quickly. The one that has access to images needs to agree with the one that works based on state. And so very fast learning based on state, but also fast agreement for the other controller that's doing it based on images, which is using this network. And so if you run this, kind of things you can do. This is the robot's point of view, is hanging a coat hanger. This is autonomous, hanging coat hanger when there is other objects that might distract the robot. This is a very tight fit, so it requires some good dexterity from the robot to be able to get in there. It's not always holding the hammer the same way, so it needs to learn to pay attention to both where the nail is and how it's holding the hammer. The coordinates it extracts after those conv layers essentially give it that information, and then it can compute motor control based on that. Do you have a question, Abhinav?
How generalizable are these policies, like even in simulation or the real world?
So these policies are specific to the task that we're looking at. So there's one policy for screwing cap onto bottle, and it works on various bottles and caps that are somewhat similar. Another one is for inserting that block into that kind of matching opening. And so there's a big open spectrum of how do you learn things that generalize beyond the skill that you were just learning right there. Absolutely. There are other architectures that I didn't talk about, but that you might want to look up. You can use LSTMs inside these actor-critic methods. You can use explicit memory. You can use auxiliary losses. So you don't get a whole lot of signal sometimes from the reward, so you can add losses like this here. You have your value function stuff, that's your Q function, but you can also have something that in a shared trunk of the neural net predicts rewards that you get at the current time, rewards that you get at the next time, and so forth. You can predict, in parallel to learning a Q function for what you really care about, you can also learn a Q function for other objectives. Because Q learning is off policy, you can reuse data no matter how it was collected. You can in parallel train many, many Q functions with a shared trunk. And you can have Q functions that are learned against very simple things like, can I control what I see in the top right pixel in the next frame? And so that gives you a lot of extra signal to build up the understanding of the world and learn a lot more quickly than if only you train on the actual reward. And so this result from DeepMind showed that it can learn to navigate a pretty complicated maze environment from first-person vision.
So these LSTM or attention mechanisms or whatever, if you put them in, what exactly are they storing in the memory?
So what they're storing here, I'm not sure. But in general, what they're trained to store whatever is relevant to make decisions in the future. And so you would hope that if an agent is navigating a maze, that it would store something about the layout of the maze. And some people have looked at it. Can you predict the coordinates of where you are in the maze based on the activations in the LSTM? Because that would, and if you can predict it in a simple way, then that means there's a simple representation of your coordinates. And there are some results showing that these kind of things happen. Okay, exploration, just one slide. The typical thing to do is just randomness, and hopefully it helps you enough. But if the rewards are very sparse, it's not going to get you there. And so then a typical thing to do is to introduce exploration bonuses. Instead of just a reward that's intrinsic to the environment, you give reward for seeing something you've not seen before. Then the question is, how do you measure that, and what does it mean that you haven't seen something before? In our work on Vine, what we looked at is build a dynamics model of the environment in parallel to learning your policy and value function. And that dynamics model is represented as a Bayesian neural net, the posterior over possible dynamics models. And as you get new experience, you can see how that posterior changes. You can say, what was my posterior now? What is it later? Take the Cal divergence between the two. And that tells you something about how informative it is, what you saw, and that's your bonus. You can also do density estimation, so you can use the latest density estimator like a pixel CNN, and you can use that to give exploration bonuses to your agent. So whenever it sees some image it's not really seen before, it'll get reward. Of course, this decays over time, because as you see that image again and again, the density associated with that image will be higher and higher. The reward will decay and decay, and you'll get less reward for seeing it again. The beauty of doing this is that it's not just that you get this reward right now, but what happens is your policy, your value function, your Q function update, and in the future, you will have learned to steer towards the types of things that are novel. Or at least that's the intent of this kind of setup. Okay, let me do 1 minute per idea here, because we have exactly, I think, 7 minutes left. Value iteration networks. Let me go to the slide here. What is the idea here? A lot of problems that you want to solve are planning problems intrinsically. So what you want to do is you want your agent to plan in an environment. But what you get in is raw sensor inputs, and it's not clear how to plan in that space. So value iteration networks do this: say value iteration knows how to plan, but the raw sensor inputs are not what we want to plan over. So what we're going to do is we're going to encode value iteration in a module inside the computation graph, put a neural net in front of it that processes the observation, feeds into the value iteration module. This then outputs values. There's an attention over the values, and then a policy that, based on that, decides what to do. And so what you do here effectively is you force the observation processing to extract something like state, such that planning against that state is a productive thing to do and can predict the right actions to do well. Value iteration itself, if you look at the math, it's essentially the same math as component math. So it fits directly into standard component architectures. And so you have effectively a fully end-to-end thing here. And you can even, for the planner here, you don't know what the dynamics are. You don't know what the reward function is. Those are just free parameters that get trained with everything else. And so effectively what you learn is a dynamics model and a reward function in here, as well as a way of representing state that combined lead to good actions. So it's a way to build in a prior on what you think should happen to learn more effectively. It can help with navigation tasks. Actually, in fact, also quite complicated navigation tasks. Some recent work in Chaitanya Malik's group has applied this together with also an explicit map that can be stored in memory to learn first-person navigation in real buildings. It's taken images, goes to LSTM. The LSTM can build a map based on that, can feed the same information into a value iteration network, which then plans against all of that. And this is all end-to-end differentiable. And you can essentially, the way it makes maps, the way it plans is end-to-end optimized to do well on these tasks. Some closely related work on embedding to control, where instead of value iteration in the middle, you put LQR, which is a standard optimal control method, in the middle. You can do the same thing. Predictron is the same idea more or less as value iteration networks, but it's coming from the other direction. It's instead of having value iteration, which solves a planning problem, it says, I'm going to solve a search problem. I'm going to look at where am I at right now. If I have a dynamics model and a reward function, I can predict the reward that will happen at the next time, at the next time, and so forth. I can predict all of those looking into the future. I don't have a dynamics model. I don't have a reward model, but I'm going to train them to be good at predicting those things and then use them to plan against. So, and then the kind of results they've shown is that you can plan how to hit a billiards ball to get other balls into the hole as you'd like it to go. The key idea here is that what you're learning is, or the key starting point I would say is, if you just learn a dynamics model, it's very easy to spend your representation resources on the wrong thing. You could spend them on modeling how the leaves of a tree move rather than what you actually care about, are you colliding with the tree or not? And so what this does, it zones in on predicting rewards and values, which then means that the observations get processed with that in mind rather than arbitrary future properties. You can also modularize these things. This is some work that we did at Berkeley. Imagine you have 2 robots, 2 tasks. You'd hope that you can have a network associated with each robot, a network associated with each task, and then mix and match to solve new things that you haven't trained for. And so those are the kind of things we looked at, and actually works reasonably well, where you would, for a new task, grab the modules that you need, sequence them together, and of course at training time you do the same thing to train these modules to be good at being sequenced together in this way. But then at test time, you take a robot task combination you've never seen before and test that it still works. The Option-Critic Architecture. So earlier we talked about hierarchy being relevant to reason over longer timescales, because otherwise you don't get enough signal potentially. Option-Critic Architecture, what does it do? You have an environment still. You have a critic here. Critic is the thing that computes the value function. You have low-level policies here. These low-level policies, one of them is currently active and chooses what to do. But the high-level gates, which one of these is active? The low-level policies act. They have a termination condition. When they terminate, the high-level gets to choose which one goes next. And so that way you get some kind of notion of the high-level thinks about longer horizons and the low-level thinks about shorter horizons. And in combined, it can learn more quickly than if you just had a flat architecture. Here's another one. I think this one has probably some of the most promising results recently in this line of work. This is building on Diane and Hinton's work from '93, Feudal Networks. The idea here is that the way to get something done is you tell somebody else to do it, and that somebody else tells somebody else to do it, and so forth. If you work that way, then the person at the high level doesn't need to know much about what happens at the low level. They can just say, hey, I want some outcome. And the level below can decompose it a little bit, and so forth. That way, you can essentially decompose things in a hierarchical way where you maybe never need to reason over more than 10 time steps at each level, where time steps at each level are different time discretizations, of course. And so what is this architecture here? Let me take 2 minutes for this one, actually. You get in state. You process it with some neural net to get some more meaningful representation of state, because this is pixels and it's not that great to work with. You process it some more in this top pipeline, which is the manager. And the manager has an internal state representation. Internal state goes into the LSTM, which keeps track of some history of state. And then this goes into a goal setter. The manager says, I'm going to set a goal, and the goal will always be of the type state at time t plus c minus current state. So that's what the goal is, and says, this is what I want. I want this change in state. Of course, this state is internal to the manager. This worker over here doesn't really know this state, but gets that set as a goal, projects that down into their own space with just a matrix operation, linear operation. Then that results in a weighted sum of distributions over actions. So for any state, the worker below generates a distribution over actions, but many distributions over actions. Just like in the Option-Critic, where there's multiple policies, you can think of it as there's multiple policies. Each generates a distribution over actions. And this thing here then selects, in a weighted way, from the distribution over actions, what action will be sampled. What's interesting here is that the high level sets goals. The low level tries to achieve goals. So the low level runs everything we've seen so far. Actor-Critic, so value function policy gradients, and does the standard updates over here. A is the advantage, is reward minus value. So that's what we know. But reward is defined here as how well do you satisfy the goals set by the level above you. And so it learns to satisfy the goals that are being asked for. The question is, what goals should you be setting? That's kind of the novelty in this paper here that just came out. This is how the high level updates. Let's first forget about this and see what naively the high level could do. Naively, the high level could run a standard policy gradient. It could say, I'm outputting an action. This is my action. I want to increase the grad log probability of my action based on the advantage I experienced. If you do that, it kind of is not really aware of what the effect of that request was. And so it works a lot better. They do ablation studies for this. If the high level updates based on this equation, which is saying, whatever happened, advantage measures how good that was, because the high level sees the real reward. How good was it what happened compared to average? And then update my goal setter architecture to set goals that are closer to whatever just happened. So the naive policy gradient would say, do more of what you just did. this policy gradient says do more goal setting according to what just happened rather than what you asked for. So in the beginning, the worker will not achieve what was asked for, and so this is drastically different. The manager will say, whatever happened, that's what I should have asked for if it was a good thing, or not if it was a bad thing. So that's the fundamental difference between standard policy gradients and what's happening here. Okay. Now let's, in the last 2 minutes, switch to completely different things. In deep learning, a lot of people are excited about it because you learn a representation, you can reuse it. You train an ImageNet, you reuse it in another task, and it still works. What is the equivalent for motor control? So in RL, we don't really have the kind of setup where we have something large scale, a lot of diversity, and we evaluate on generalization. Instead, the typical evaluation is small scale, emphasizes mastery, and is evaluated on performance. How well do you play Pong after learning? Not how well do you learn a new game after you learn Pong. But that's actually what we maybe want. It depends. Sometimes you want mastery, sometimes you want generalization. So the question is, if you want really good representations that are general, we should probably focus on generalization rather than mastery. So how do we get there? Well, here is one way to do this. We set up a network theta, and we'll feed in different tasks. And when we feed in a task, there's a standard policy gradient update that we could do. This leads to a new parameter vector theta prime. What we want is we want it to be the case if we had a good network, a good initialization from which we can fine tune. What that means is that if we do just one gradient update, that's enough to master a new task. Okay? That's what people do in fine tuning on ImageNet. A few gradient updates and boom, they solve a new task. So that's what we want. So we want that to happen, one gradient update to be good. So we want the learning to be not to master one task, but actually be a gradient on the gradient update. We want to learn a network such that after a gradient update, we do really, really well. So we take the gradient of the result of the gradient update, and that's the parameter vector we want to find that does well for this. If you do that effectively, pictorially what's happening, imagine there are 3 tasks. There's one that the optimal parameter is here, here, and here. What you want to do is you want to move into the middle, because from the middle, it's likely that a gradient update will push you right onto where you need to be for task 1, 2, or 3, depending on which task you're faced with. Okay? So what happens here is after training, this is what the policy is. Why is it just fiddling in place? That's actually an exploration strategy. It's learned that if it's going to run something with this network, from that data, do a policy gradient update, that is going to be a really good result for whatever the reward function was that was infused during that data collection. And if we infuse forward motion, this is what we get. Just after one gradient step, it's learned forward motion. If the reward is related to backward motion, after one gradient step, it learns backward motion. Typically, you need thousands of gradient steps on these things to get anywhere, and that corresponds to thousands of experience collections. And this learns in just one experience collection to solve a new task. Of course, related to the training tasks. This actually also works for classification. We want to do this for RL. It turns out there's a lot of work in classification on few-shot learning. Often the test is on something called omniglot, where you have 10,000 different characters. You're supposed to recognize a new character after having seen it only once or maybe a couple of times. And so training time, you get 5,000 characters. You're supposed to train on that. You can learn on those 5,000 to become good at seeing one that you haven't seen among those 5,000. And at test time, you get 5 new characters, one example of each, label with each one, and you're supposed to immediately know what each one is when you see future examples. And it turns out this very simple setup outperforms a lot of networks that were designed specifically with classification in mind, that say, oh, I have a memory architecture, I have a matching network, or 2 things of the same class, all kind of things that are specific to classification. Just doing this gradient on the gradient update type learning gets you better performance on all of these tasks in classification. It also works on regression, which a lot of these don't apply to. Okay. So here's another example. On the left, you see after meta-learning, then after just a few rollouts and one gradient update, it knows how to go backwards in the backwards environment and forward in the forward rewarding environment. It even celebrates this one. So last thing I want to say is RL squared. I think the main bottleneck right now in reinforcement learning is not that things maybe cannot be learned. It's more that the learning takes enormous amounts of time. So DQN is better than a human, but it takes maybe 40 days, and a human learns a game in 2 hours. This kind of mammal approach that I just showed you might get there by learning new things very quickly. But what I'm going to look at here is something even more meta than that approach. want to learn fast. Traditional algorithms are happy to solve any problem you put in front of them, and that's great. But the things you encounter in the real world is a tiny, tiny subset of things that you can mathematically define. And they apply to anything you can mathematically define, and the real world is a tiny subset of that. So the question is, can we design algorithms that exploit the fact that the real world is a tiny subset of that? So the questions are, can we build a good prior for real world MDPs, maybe games for now, and can we design algorithms that make use of such prior to learn more effectively? The key idea here is that we're going to learn everything. So we're going to essentially put down a big recurrent neural net, and that recurrent neural net is supposed to encode prior and reinforcement learning algorithms, such that when you deploy this recurrent neural net in a new situation, it's just running, and by running, it's running learning, and it's using prior information that's encoded in the weights, and it's running learning by it's changing the activations in the recurrent units, and through that, adapting very quickly to new situations. So we need, I'm going to go through this somewhat quickly. This is the picture. RL squared, the RNN is the policy, but also gets access to observations and rewards, and will be trained on many different environments, and is trained to do well when faced with a new environment. A lot like the model agnostic meta learning, you're trained to do well in a new situation rather than trained to do well in your current situation. Show you some results. It does as well as carefully designed algorithms for bandit problems, at least as long as there are not too many bandits at play. It does as well as carefully designed Bayesian optimal algorithms for small MDPs. These are sanity checks that effectively you can learn an algorithm that's as good as the best designed algorithm so far. And then for maze environments, it's also able to learn good strategies for mazes. What that means is the following. During meta learning, it doesn't know yet what to do. You kind of just wander around. But then once you've been trained, this is what happens. You've been trained to do well when being in a maze only twice, or twice in this case. So you learn that you need to navigate the maze quickly to see where the goal is, and then you get dropped again. You need to have remembered in your activations of your recurrent neural net what the map of the maze was, such that you can now navigate to the goal super quickly and get maximal reward. So it's specifically trained to get dropped in new mazes and do this. All right. I think I'm going to wrap up here. If you want to try out some things yourself, this is potentially a good place to get started code-wise. Thank you.
We're running a little past for lunch, but let's take a couple questions now before we break, and then more questions for Pieter.
Yes?
Can you explain how the information of any updates on gradients of frequency to the other?
Okay, the gradient on gradient, how that works. So I definitely went a little fast. So what happens is, what we care about, yeah, I guess there's an L missing here. Sorry about that. So there should be a loss function here. But what we care about is effectively the loss after an update has happened. So we know that when we're getting deployed in a new environment, a gradient update will happen. This will result in a new theta, theta prime, which is the original theta plus an update. That will incur a loss. That L is missing here. Sorry about that. There's a loss here, and we want to minimize the loss incurred there as a function of the original theta. So we're saying we want an original theta such that if we use it later against a loss function that we don't know yet, so we sample a lot of different loss functions here at training time, such that it becomes really good for any new loss function. So it's supposed to generalize to new loss functions to be really good at, with one gradient update, adapting to the situation and do well. The main intuition here is I mean, there's other work that doesn't specify the update rule. There's some work by Hugo La Rochelle, I forgot the other author, his name, that does something like this, but they leave it completely open-ended, what your update rule is. And the intuition here for us, and actually we compare with them in some of these plots here, the main intuition for us to go with this is that the results on ImageNet suggest that there is a way to train a neural net such that it learns representation, such that gradient updates are a good thing to do to succeed. It's a nice prior that compacts what you're going to do in your update, as opposed to having some giant LSTM that can do whatever update it wants, and then you need a lot more data and might even not be that well conditioned to find out what your update rules should be and what your weights should be. And so we started from the ImageNet observation and said, if we just keep it this simple, as what people mostly do in practice, but we train specifically with the end goal in mind rather than after the fact saying, hey, somebody trained an ImageNet, let me now reuse it, see what happens. Thank you.
We have about an hour and a half for lunch. All the speakers, whoever is around, will also be available during the panel, which is around 4 or 4:10 or so. So they'll